Welcome to Time Pilgrimage! Today, we are going to explore the fascinating world of neutron stars, the most extraordinary objects in the universe. In the vast cosmic theater, where stars twinkle like distant diamonds and galaxies dance in a graceful celestial ballet, few phenomena capture the imagination quite like neutron stars. These enigmatic celestial objects stand as monuments to the cosmos's most breathtaking extremes. Both in density and in the drama, they unfold on the stage of space. Neutron stars, the remnants of massive stars that have undergone a cataclysmic supernova explosion, are the stuff of science fiction dreams turned mind-boggling reality. The formation of neutron stars is a spectacular cosmic event, born from the explosive demise of massive stars. This process is a remarkable ballet of gravitational forces, nuclear physics, and the unforgiving pressures of the universe. Let's dive deeper into how these extraordinary celestial objects came into existence. It all begins with the birth of a massive star. These stellar giants have a much higher mass than our sun, typically 8 times or more. Throughout their lives, they burn hydrogen into helium through nuclear fusion, releasing an immense amount of energy that keeps them shining brilliantly in the night sky for millions of years. As the massive star ages, it undergoes a series of nuclear fusion reactions, transforming lighter elements into heavier ones. This continues until it reaches iron in its core. Iron is unique because it cannot be fused into heavier elements without requiring more energy than it releases. When a significant amount of iron accumulates in the core, the star's nuclear furnace begins to falter. With the core predominantly composed of iron, the star reaches a critical point in its life cycle. The immense gravitational pressure generated by its own mass can no longer be counteracted by the energy produced from fusion reactions. The star's core begins to contract rapidly under the relentless pull of gravity. The core's contraction reaches a point where it becomes super dense, and the iron nuclei are pushed closer together. At this moment, the core collapses inward at an astonishing speed, triggering a cataclysmic explosion known as a supernova. The outer layers of the star are blasted into space in a brilliant burst of light and energy while the core implodes. In the heart of the collapsing core, something incredible occurs. As the core shrinks to just a few kilometers in diameter, the intense pressure causes protons and electrons to merge together, forming neutrons. The core is now composed almost entirely of densely packed neutrons, and it becomes a neutron star. This process happens in a matter of seconds, and the resulting object is extraordinarily dense and compact. The explosion of the outer layers during the supernova disperses heavy elements, enriching the surrounding space with elements like gold, silver, and uranium, which were forged in the dying star's core. When a massive star exhausts its nuclear fuel, it can no longer withstand the crushing force of its own gravity. In a blink of cosmic time, it implodes, compressing all its mass into an unimaginably tiny sphere just 20 kilometers in diameter. The result is a neutron star, a stellar object so dense that a mere teaspoon of its material would weigh as much as 1 billion metric tons, enough to make even the most massive earth-bound structures seem trivial. But the density of neutron stars is just the beginning of their astonishing tale. These stellar remnants possess magnetic fields that defy comprehension, registering a staggering 1 trillion times stronger than Earth's magnetic force. This colossal magnetism manifests itself in a spectacular display of cosmic fireworks, the birth of pulsars. As the star collapses, it retains its angular momentum, causing it to spin incredibly fast, a fundamental principle of physics that applies to all rotating objects. This means that the total angular momentum of the collapsing core remains the same as it was when the star was intact, regardless of its size or density. Since angular momentum is conserved, and the core's radius decreases significantly during the collapse, the core must spin faster to maintain the same angular momentum. This is similar to how an ice skater spins faster when they pull their arms closer to their body. As the core continues to collapse, it reaches such extreme densities that protons and electrons combine to form neutrons, giving rise to a neutron star. This newly formed neutron star inherits the rapid rotation of the collapsing core. This conservation of angular momentum causes the neutron star to rotate rapidly, and the emission of radiation from its magnetic poles creates the characteristic pulsar behavior that astronomers detect and study. This spinning action persists for millions to billions of years, depending on the neutron star's initial conditions and interactions with its environment. Neutron stars often have powerful magnetic fields, The combination of their intense magnetic fields and rapid rotation results in the emission of focused beams of radiation from the star's magnetic poles. These beams of radiation are what we observe as pulsars, as they sweep across our line of sight like cosmic lighthouses. These beams sweep across the universe with each rotation, casting rhythmic pulses of energy, hence the name pulsar. Yet the most mind-bending aspect of neutron stars is their capacity to bend the very fabric of space-time itself. Their gravitational pull is so intense that it warps the surrounding space and time, setting off ripples known as gravitational waves. In a groundbreaking discovery that electrified the scientific community and the world, these elusive waves were first detected in 2015 as predicted by Albert Einstein over a century ago in his theory of general relativity. This confirmation opened a new era of astrophysics, one in which we could directly observe the cosmic waltz of black holes and neutron stars through the lens of gravitational waves. As if these celestial marvels needed any more intrigue, neutron stars are also cosmic alchemists. Deep within their ultra-dense cores, they forge some of the universe's most precious elements, such as gold and uranium. When neutron stars collide, they trigger titanic explosions called kilonovae, sending these newly created elements hurtling through the cosmos. These cosmic collisions are like the universe's own treasure chest, scattering rare and valuable elements across the heavens. Despite the wealth of knowledge we've acquired about neutron stars, a shroud of mystery still envelops these extraordinary cosmic entities. Scientists remain relentless in their pursuit of unraveling their secrets, launching space missions and building cutting-edge observatories to further our understanding of these celestial enigmas. The newborn neutron star is a mind-boggling cosmic entity. Thank you for watching. Please subscribe and smash that like button.